Hi everybody, I hope you're doing well. My name is Omaima Benkhadda. I'm a PhD student in the Faculty of Sciences and Technology of Milan. My presentation title is Design and Analysis of Rectangular Microstrip Patch Antenna using different feeding mechanisms for 2.45 GHz applications. The presentation plan is organized as follows. First, introduction, then microstrip antenna design. After that, we will present the different feeding mechanisms, simulation and results, and finally conclusions and future works. Recently, microstrip antennas are spreading widely in all the fields due to their low weight, easy miniaturization, portability, good performances, and low manufacturing costs. This kind of antenna is used in different applications like mobile communication, Bluetooth satellite communication, and so on. The transmission of electromagnetic energy to a microstrip patch antenna can be done by different techniques, and this technique will affect the antenna performances. Then, the choice of the appropriate feeding method depends on the application's domain of the microstrip antenna. The aim of this work is to present a comparative analysis between the several feeding techniques of a rectangular microstrip patch antenna operating under 2.45 GHz. A microstrip antenna can be designed by analytical methods such as transmission line method or cavity method. These techniques have difficulty for complex structures, the reason why many numerical techniques have been used, like the method of moments, the finite integration technique, the finite element method, and the finite difference time domain. In this work, we will be using the transmission line method and the method of moment. The dimensions of the rectangular microstrip patch antenna are calculated using the transmission line method, where the width and the length of the patch are calculated using the following equation, where c is the light speed, fr is the resonant frequency, epsilon r is the relative permittivity, epsilon effective is the constant of the dielectric of the substrate, h is the height of the substrate, and delta L corresponds to the increase in length of the antenna due to fringing effects and is given by equation number 4. There are various feeding techniques for a patch antenna that can be classified into two categories, which are contacting and non-contacting techniques. In the contacting methods, the antenna can directly feed with radio frequency power using the contacting element as coaxial connector in the coaxial probe feed or a microstrip line in the microstrip line feed or CPW feed. In the other hand, in the non-contacting techniques, the electromagnetic field coupling is done to transfer the power between the microstrip line and the radiating patch. The most used in non-contacting techniques are the aperture coupled feed and proximity coupled feed. The structure of the designed microstrip antenna is composed of a rectangular shaped patch of length 28.83 and width 37.13 mm printed on a substrate FR4, the relative permittivity of 4.4 and the thickness of 1.6 mm. This antenna will be performed with Catficom, one of the famous softwares based in the method of moment. First, the rectangular microstrip antenna will be fed by a coaxial probe technique as shown in figure 7. The feeding probe is placed at the point F, and the distance between the center of the patch and the point F, YF, is equal to 7.5 mm. The simulation results for the reflection coefficient is depicted in figure 8. The resonant frequency is obtained at 2.31 GHz, 132 MHz lower than the resonance frequency given by the transmission line method, And in order to have 2.45 GHz as resonant frequency, the design is optimized by the method of moments, and the new dimensions are 35.11 mm and 27.13 mm. The reflection coefficient for the optimized antenna is shown in figure 9. The resonant frequency is 2.45 GHz with a reflection coefficient of minus 20.01 dBA. And figure 10 shows the effect of changing of the feed position on adaptation. 5 values for YF were tested. The simulation have confirmed that the best value obtained to have the good impedance matching is YF equal to 6 mm. And figure 11 illustrates the 3D radiation pattern. We note that the maximum gain is 6.29 dBA. The same patch antenna is fed by a microstrip line with an inset of length Y0 equal to 6 mm, and the characteristic impedance of the microstrip line is equal to 15 ohm and is calculated by the following equation, where WF is the width of the microstrip line and H is the height of the substrate. Figure 13 shows the variation of the antenna S11. It's observed that the resonant frequency is 2.48 GHz with a reflection coefficient of minus 25.28 dBA. A parametric study is done to know the effect of the length of the inset. As shown in figure 14, the better impedance matching is obtained when Y0 equals to 9 mm. The 3D radiation pattern of the antenna is shown in figure 15 with a maximum gain of 6.45 dBA. In the CPW feed, the ground plane and the microstrip line are placed on the same plane as the patch. The S11 acquired by this technique is presented in figure 17. We observe that the resonant frequency is 2.68 GHz, 212 higher than 2.45 GHz, with a reflection coefficient of minus 13.84 dBA. And figure 18 shows the 3D radiation pattern of the antenna. The gain is omnidirectional and the maximum simulated gain is 1.88 dBA. In the aperture couplet feed, two dielectric substrates are used and the ground plane is placed between them, where the microstrip line is placed on the bottom of the two substrates as shown in figure 19. The relative permittivity of the top substrates is 4.4 and 3.3 for the bottom substrate. The S11 of the antenna is shown in figure 20, and the antenna can operate at 2.44 GHz with a reflection coefficient of minus 32.77 dBA. And the 3D radiation pattern is given in figure 21 with a maximum gain of 5.56 dBA. Also in the proximity couplet feed, two dielectric substrates are used and the microstrip line is placed between them, where the ground plane is placed on the bottom of the two substrates as shown in figure 22. The simulation results for reflection coefficient is depicted in figure 23. The resonant frequency is obtained at 2.48 GHz with a reflection coefficient of about minus 34.57 dBA. And the 3D radiation pattern is presented in figure 24 and the maximum gain is 6.65 dBA. The table gives a performance comparison of the designed antenna with the several feeding techniques. The CPW feed technique increases the bandwidth into 615 MHz and have a low gain. The coaxial probe feed and microstrip line feed techniques have a low bandwidth and high gains. The aperture and proximity couplet feeds provides a good impedance matching with a medium bandwidth and a high gain. In terms of conclusions, the microstrip antenna is one of the best solutions to design simple, low-profile and miniaturized antenna. The design of the microstrip antenna with the appropriate feeding technique will depend on the antenna's performances and its applications domain. As perspective of this work, a comparison between the different feeding techniques will be done for microstrip array antenna. Thank you for your attention.